Hi everyone, welcome to the presentation. We're gonna present the deep neural network model that is used to predict the ticket price for a sports event or a concert event and so on. And the major challenge of this of modeling data in this scenario is that the data is very sparse in terms of both spatial information and temporal information, as I will explain later. And I'm Fei. This work is done together with Hao when we were both at GE. So what we are trying to do here is we are trying to forecast the ticket price of a particular event. And this event can be a sports event, such as a hockey game, a soccer game, or NBA basketball game, and so on, or a concert. And to be more specific, we're trying to predict a price for all these seats in any time before the event has taken place. So in the end, you should know that from this time on till the event has started, what the price of every particular seat will be in this event. So the application can be so there are a lot of applications. One is that if you are the event holder, you can use this to plan your campaigns. For example, if the model tells you the price is going to go up in 2 weeks, you may be able to plan an event that is upcoming in 2 weeks, so that you can sell the tickets at their peak price. On the other hand, if you are the user, you can use the forecast to see when the ticket price will drop so that you can buy them. And also you can use this for budgeting if you are the event holder, and so on. So there are several challenges regarding this problem. One is that if you think about the price of the price of a seat in an event, the price should behave as a time series, so that the price will change according to time, according to the date to the event. And also you would think that the neighboring seats would have similar prices. However, if you are more in the back, you should pay less most of the time, and also you are more on the side, you also pay less, and so on. And also we observe that each event would have very different price according to who is playing in that event. For example, for a soccer game, if your team is playing a very good team that has a lot of star players, the event will become very expensive overall. And also that there is typically historical information in your data. For example, we have an event upcoming in 2 weeks from now, and today I already know that I have sold tickets in the past and how much those tickets were. So that those information actually should be able to help the model to know what the future prices will be. And in addition to that, there are actually the data are very, very sparse. This is because if you think about the ticket price for a seat as a time series, you will not observe any of the transaction except one data point most of the time. So you will not be able to observe any of the price unless the ticket has been sold. And after the ticket has been sold, you also don't know its price, how much the ticket will be as well. So there are actually the data actually are very, very sparse in terms of time, and also in terms of space as well, because not all the tickets are sold all the time. Sometimes some of the tickets are not sold, so that you will have no data for those tickets or for those seats. And also the features for your data actually comes on different levels. You have seat level, which in which that your features will change for each seat, because each seat will have different row number, different column number, and so on, so that every seat is different. But all the seats in one event should share features that are common to all the events, such as if the event is on a Sunday, or if the event has a very famous performer coming to play, or the event or it's a sports game that is very crucial, and trying to decide who is going to the finals and so on. So that event feature is being shared by all the seats in that data set. So here is one of the illustration of how the data sparsity works. So this is one of the seat, and this is taken from the NBA games, and it has a lot of events. So the ticket for this seat has been sold multiple times throughout all the games. There's about 246 of all the games, and we plot on x-axis the date to the event. And you can see that in this histogram that most of the tickets has been sold when you are very close to the event, and very few number of tickets has been sold when you are more further away from the event. So this illustrates the sparsity in the temporal place for this seat. So to deal with the sparsity of the data, we use two methods. So first, on the temporal space, we condense the data by taking the log and then binning the data. So the top left shows you the similar illustration as we talked about in the previous slide. But this is for all the tickets that has been sold. So you can see that it has a very long tail to the right. So we first take a log of the time to the event. Then and then you can see that this becomes much less spread out as the first slide. And then we take a bin of the time, so that for each time, for each bin, there can be multiple events in that bin, but we treat each bin as one timestamp point. And to decide the number of times bins, we actually try different numbers, so which is shown on the plot on the right, and then look at the map of the model and see how the accuracy will be. And then we can decide, okay, so taking 20 bins gives us the best result. So we use 20 bins to bin the data. So the other approach we take to condense the data in terms of space is that we look at the sections of the stadium. For example, here is the basketball court, and here are all the seats. So typically a basketball court has been divided into multiple sections, balconies, lodge, and so on. And in each section, there are a lot of seats inside. And most of the time, the ticket price within one section does not change too much. So within one section, the price are similar to each other. However, from section to section, the price may differ much more. So the section more in the middle are most likely to be more expensive, and the ticket price for seats in the back are most likely to be less expensive, and so on. So by condensing the seats into sections and also bin data according to time, we are able to obtain a much less sparse data set. Because you can imagine here, for each one of the sections, all the tickets that had been sold inside this section will provide us with a value, or a ticket price value for that section in total, so that as time goes by, you will have much more transactions that is known to you. So by doing both the condensation on the time level and also the space level, you will obtain a much condensed data set, which is much less sparse. So the slide here shows the model structure. So this model actually has four parts. The first part is the correlation, or the condensation um, um, method we talked before, which condenses the data in terms of both time and space. And the second part of the model, actually, we call module 2 here, is actually use the convolution neural network on the spatial level. This is actually to model the section and the differences of prices in the sections using convolution neural network. And the third part of the model is actually a recurrent neural network, and we were using this recurrent neural network here to capture the time series aspect of the model. So both module 2 and 3 together, the intuition is that if you think about the ticket price per section as a pixel with different values, so that the actually the values of pixel will change over time. So overall, if you look at the entire stadium or arena, for all the seats that's in there, or the seat section that's in there, you can think about this as the price of the seats will change just like a movie throughout time. So to model the movie, which has both time and space information, we use a convolution neural network combined with the recurrent neural network. So that was intuition behind it. And then actually after the modeling on the condensed level, we actually have more neural network layers that expand the condensed layer back to its original scale, which is per seat instead of per sections. So the reason for that is that we know that now we have some prediction for the price for the section, and then we can add information such as where the seat is located in this section is more in the front, which most likely to be more expensive, or more in the back, which column it is, and so on. So we can use that information to further infer how much the price for the seat will be. So by doing this, you will actually get the ticket price at the seat level. And for the loss function, we actually use two loss together. One is the loss on the last layer, which is the loss on the per ticket per seat level. And then we also have another loss on the condensed section part. So combining those two laws together, then we train the overall neural network. And to benchmark our model, we compare it with different approaches. So we compare it with some simple approach, such as taking the median price for the gain and the median price per section, and also use a linear method and the random forest and the XGBoost. We also compared using with approach using just recurrent neural network. Here is the GRU method. So all of those methods are shown in green, and the red ones are our framework, but with different compositions. So the first one is without temporal modeling, then the second one is without spatial modeling, and the third one is with only one loss function, which is the last loss function in the last layer, and the deep red one is our model. And the difference between the matrix in the upper and in the top and the bottom figure is that the first one is the mean square error as a matrix, and the second one is the MAPE as a matrix. So by comparing those results, we see that actually our model outperforms all the rest of the approach, and it shows that it's actually crucial to include all the part of the framework: temporal, spatial, and also the two of the loss functions. And actually, very interestingly, you can see that the recurrent neural network by itself, showing on the last green bar on the right, shows you that actually its performance is not very good. And we think this actually is very likely because the data is so sparse, is very sparse, that the model actually is having trouble trying to converge and come up with a good model, so that the performance is not very good. Actually, it's worse than most of the other approaches. And by actually having the condensation part, which condense the data to give us a much less sparse data, the model performance has improved. If you just look at the lighter red plot here, and combining all of the components of the model, it actually shows the best result, which is showing in the deep red bar here. Thank you very much. Please let us know if you have any questions. We can reach by both the author, me, and Hao can be reached by the email on this paper. Thank you very much.